well, we say, okay, what is S11? S11 is V1 plus by, sorry, V1 minus by V1 plus when V2 plus equals 0. And how do you ensure that V2 plus is 0? Right. I mean, unlike in the admittance parameters where you terminate the port 2 in a short, right, here you want to make sure that, you know, V2 minus is what this linear 2 port is pushing onto the output port. You want to make sure that V2 plus is 0, and that's only possible when you terminate the output port with the resistance which is equal to the characteristic impedance of the line, right. So, the test setup therefore is you have our 2 port, okay. So, we have some voltage source here, and then we have this transmission line, and then we have another transmission line here. The length of these lines can be 0, this is Z0 and then this is Z0 and this is Z0, and so this is V1 plus, right. What comes back is, what comes back? Right. So, this is basically, this V2 plus is 0 because you have terminated the output port, right. So, this is S11 times V1 plus, all right. And so, all right. So, what comment can you make about the V2 minus now? Is it 0 or is it non-zero? It's non-zero because, well, the 2 port is basically whacking this the second port, I mean the output port. So, this is basically S21 times V1 plus, right. And this is analogous to what we do with the Y parameters and so on. What would we do? We would, in the first experiment, we will short the output port and excite the input port with a voltage. The input admittance gives you Y11, and the current in the output port measured will give you, the ratio of that to the applied voltage will give you Y21. Similarly, here, you terminate the output port, you excite the input port. What's reflected, or in other words, S11 is the input reflection coefficient. I hope you remember that V1 minus by V1 plus is the reflection coefficient. So, the input reflection coefficient with port 2 terminated. All right. And S21, I mean, can we make any comment about S21? Do you, what parameter of the 2 port do you think it would be related to? Yeah, it depends. I mean, S21 is basically quantifies within quotes the gain or Y21 or whatever, the forward transfer parameter of the 2. Now, okay, so okay. Now, likewise, what about S22? Its output reflection coefficient when when port 1 is terminated with Z. They are clear, people? All right. And what comment can you make about S12? What does that quantify? I mean, just like Y12, what does Y12 quantify? It quantifies the effect of an excitation at port 2 on the response at port 1, right? And likewise, S12 basically is telling you, if I throw something at port 2, how much of it comes out of port 1, right? So, this is again quantifies the amount of feedback within the device. Okay. So, a caveat, we've assumed identical characteristic impedance at both ports, okay. In which case it is, it turns out that, it does not matter. I mean, you can simply use the amplitudes of the forward and backward voltage waves. Strictly speaking, the definition of the S parameters is to define first an incident within quotes wave, which is actually normalized to the characteristic impedance in this way, right? And similarly, the reflected wave is basically V1 minus by square root Z0, okay. And you find ratios of B1 by A1 and B2 by A2. If all the port impedances, characteristic impedances are the same of all the transmission lines connecting both ports 1 and 2, then the square root Z0 is redundant, and it simply you can simply talk about V1 minus V2 minus V1 plus and V2 plus. Okay. Sometimes these are often also called power waves. And why? The square of this directly gives you power. Okay. All right. So, if all the impedances are the same, there is no point in carrying that square root Z0 all the way. This is something just to bear in mind, right, and not get all flustered when you see, B1, A1, I mean whatever, B1, B2 equals S matrix times A1, A2, right. It is in most cases it is one and the same. All right. So, now that we know what these S parameters are, let us try and find the S parameters of some commonly used 2 ports, right, and this is analogous to the first thing you do. The first time you do Y parameters, you basically throw some example networks and find the Y parameters, and the same thing you would like to do with the S parameters, right. So, this is, let us say you have a transmission line of length Z0 and length of characteristic impedance Z0 and length Td, and you would like to find the S parameters of this guy. What do you think we should do? What would it be? Well, to find S11, what would you need to do? Okay, you terminate port 2 with Z0 and find the reflection coefficient at port 1, right. If you terminate port 2 with Z naught, what is the impedance looking in here? It is Z naught, very good. So, what comment can we make about the reflection coefficient at port 1? What do we understand by the reflection coefficient? Remember, the reflection coefficient is nothing but gamma is Z minus a gamma in is nothing but Z in minus Z naught by Z in plus Z naught. So, if the looking in impedance is Z naught, then what comment can we make about S11? It is 0, alright. Okay, and this is a symmetric 2 port. So, if S11 is 0, what comment can we make about S22? Is also 0, right. Now, the next thing to do is find S12. So, what do? We have some V1 plus here, correct, okay. And if this is remember that the reflection coefficient is 0, okay. So, there is basically you have some incident wave here. This is V1 plus. What comment can we make about the forward wave there? Pardon? It will be simply V1 plus e to the minus s times Td, or if you are doing j omega, it is minus j omega Td. And so, therefore, what comment can we make about the forward going wave here? I mean, imagine that this is a infinitesimally small transmission line. What is continuous across boundaries? Voltage, not impedance, folks, come on. Current and voltage are always continuous across boundaries. When you go from one transmission line, you have a junction and you go elsewhere, KCL and KVL must be valid at every point, correct? Okay. Here, well, we know that the reflected wave, what is the reflected wave here? We know that it is 0 because everything is terminated, right. So, the voltage here, what is the total voltage at this point? It is simply the sum of the forward and the backward waves, which is simply V1 plus e to the minus s times Td, right. And likewise, on this transmission line, we know that there is no reflected wave. So, the voltage at this point is the same as the voltage at this point, and that must be simply equal to the amplitude of the, whatever the forward going wave there, correct. So, what comment can we make about about S 21? It is simply e to the power e to the minus s T d, or on the j omega axis it is e to the minus j omega t. And of course, now this being a symmetric 2 port, now what do we expect for S12? It is the same thing, e to the minus s times t. So, the S matrix, therefore, the scattering matrix of this 2 port, now I can remove all these extras. Is 0, 0, e to the minus s times T d and e to the minus s times t. All right. Okay, excellent. Let us do another example. Let us say we have an impedance Z here, which is not to be confused with Z naught, which is the characteristic impedance of the transmission lines. So, what is S11? Please sit and calculate it. Come on, people. What is the definition of S11? What do we need to do? We terminate port 2 with Z0, and we would like to find the input reflection coefficient, right? I hope all of you are aware of why S11 is the input reflection coefficient. It is the ratio of V1 minus to V1 plus, when you terminate port 2, and V1 minus by V1 plus is nothing but the reflection coefficient, right. So, what is it? What is it now? Is Z parallel Z0 minus Z0 by all right. Okay. So, if this is V1 plus, what gets reflected back is S11 times V1 plus, because we have terminated port 2 with Z0, correct. So, what is the voltage at this node? Pardon? V1 plus times 1 plus S11, correct. So, that is evidently the voltage also at node that is the voltage at port 2, correct. And therefore, what comment can you make about the forward going wave here? Pardon? Why am I interested in this forward going wave here? That is, that is V2 plus or minus? V2 minus, very good. Okay. So, what comment can we make about V2 minus? It will be equal to the voltage at port 2, which happens to be V1 plus times 1 plus S11, correct. So, what comment can you make about S12 therefore? One plus S11. So, that is S21, sorry, is V2 minus by V1 plus, which happens to be 1 plus S1, and S12 is the same as S21, is 1 plus S11, all right, and S22 is same as S1. That makes sense? Okay. All right. So, now if Z is a capacitance, you can go and substitute arbitrary things for Z and get a whole lot of problems like this. Then let us do another example. Okay, if shunt is here, series can't be far behind. So, this is 1 Z, all right. Now, what is S11? Again same old, we terminate port 2 with Z0, okay. So, basically we terminate, and the input the looking in impedance is obviously Z plus Z0. So, the reflection coefficient is Z by z plus 2z. All right. So, this is V1 plus. What is reflected back is S11 times V1 plus. So, the voltage here is V1 plus times 1 plus S11, correct. So, what is the voltage here, guys? We know the voltage at port 1. What is the voltage at port 2? It's simply V1 plus times 1 plus S11, which is the voltage at port 1 times potential divider. Very good. So, that is basically Z naught divided by Z naught plus Z, correct. So, now what is S21? What is it? 1 plus S11 times Z naught by Z naught plus. What about S12? Well, the same as S11, S21, which is basically 1 plus S11 times Z naught by Z naught plus Z, and S22 is same as S11, which is Z by Z plus 2Z. That makes sense, people? Okay. So, I mean, you can keep now doing this until you are blue in the face. Okay. You can generate as many examples as you want and keep calculating, right? The next example I would like to do is something. So, let us say you have a 2-port already, right, with a known S matrix. Okay. Let us call this SA, and now I connect transmission line. So, this is Z naught TD1, this is Z naught TD2, all right. So, what are the S parameters of this new animal? How do we figure it out? Well, what is let us call this this forward wave, let us call this V1 x plus, correct, and what comes back therefore is V1 x minus, and what must this therefore be? V1 x plus times e to the power s times Td, and what comes back, the reflected wave here is V1 x minus times e to the minus s times Td. Okay. Likewise, this is V2 x minus, and this is V2 x plus, and this will be V2 x minus e to the minus s Td2 Td1, sorry, here, and this will be V2 x plus e to the STD2. All right. So, we are however interested in finding. So, V1 plus equals this, V1 minus equals this. This is V2 minus and this is V2 plus, because this is our 2 port. Correct? All right. So, how do you relate and we know, what do we know? We know that V1x minus V2x minus equals SA times V2 V1x plus and V2x plus. All right, and we are interested in finding V1 minus V2 minus equals what into V1 plus V2 plus. Correct? So, now can you help me out? Okay, very good. So, what is your suggestion? So, you say which are you talking about this equation? Okay, so what did you want to do? Okay, so what should I do? I will take, so you want me to pre-multiply this with, the suggestion is the following. It says you multiply this with a diagonal matrix which is e to the power STD1 0 0 e to the minus S TD2. So, that will give me, what will this give me? This will give me e to the S TD1 times V1 x minus, right. Okay, so what now? Or did you mean minus STD1 and minus STD2? Okay, all right. So, that should give me STD2 Vx V2x minus. So, that is basically, we know this is nothing but V1 minus this is V1 minus and this is V2 minus. Okay, very good. So, we are done with one side. This is equal to e to the minus STD1 0 0 e to the minus STD2. Okay. Now, what? How do we get, I mean, likewise, how do you get from here, how do we get yeah, so what is V1x plus and V2x plus in terms of V1 and V2, V1 plus and V2 plus? Pardon? E to the STD1 0 0 e to the s, correct? Is that right? V1x plus, oh yeah, sorry. V2x plus, yes. Are we good? Right. So, therefore, what should I do here? So, V1 minus is V2 minus is simply e to the minus STD1 0 0 e to the minus STD2 times SA times no y inverse, right. Okay. And so, what is this now? This is the modified. Does it make sense, people? Okay. I hope we not made any algebraic goof. It seems okay. All right. So, this is the augmented SA hat. So, anyway, I mean, so to find the S parameters, basically, as you can see, I mean, it's a little bit of algebra, just like finding Y parameters or Z parameters, it takes some work, right, but you should get used to it by simply by practice. Okay.